All right, get ready to explore something that's fascinated people forever: gravity.
It never gets old, right?
Never. And you've sent in a ton of stuff about it: papers, notes, even a rejection letter.
Wow, a rejection letter.
Yeah, seems like you're really trying to get a grip on this fundamental force, and you found some intriguing stuff going way beyond the usual Newton and Einstein.
Well, gravity still throws us curveballs. This Gravity Emerges paper, it points out how some physicists still bring up the hand of God to explain how gravity acts instantly across huge distances.
It's like we're still wrestling with the same puzzles that stumped Newton himself. Didn't he say, "I will feign no hypothesis," when someone tried to get him to explain how gravity works?
Exactly. He aced the math, but the how remained a mystery.
Then Einstein rocked up and turned our view of gravity upside down with general
You
relativity.
talk about mind-bending.
Right. But elegant, too. Suddenly, gravity isn't a force in the usual sense, it's a warp in space-time itself. Objects aren't pulling on each other, they're just cruising along the curves made by big objects.
And it explains things like gravitational lensing so well.
That's where light bends around massive objects.
Yeah, like a cosmic magnifying glass. We've seen this lensing tons of times. It's a huge win for Einstein's theory.
But even Einstein's masterpiece has its limits. This brief assessment paper you sent, it mentions how general relativity hits a wall when you try to make it work with the quantum world, the realm of the super tiny.
Right, and those singularities and black holes, points of infinite density, they give a lot of physicists a headache.
It's like the math just breaks down there.
Exactly, like we're missing a big piece of the puzzle.
Which brings us to some of the wilder theories you've included, like push gravity. I was floored when I first read about the Fatio-Lesage theory.
It's a mind bender, isn't it?
Invisible particles bombarding us from all sides, creating an inward push that we feel as gravity. It's wild.
What's really cool is that it's one of the few theories that actually tries to explain the mechanism of gravity, not just describe what it does.
It's bold, no doubt. It got some serious pushback, too. Maxwell, the physics giant, he worried about the heat this particle bombardment would create.
He had a point. If this was true, wouldn't things be heating up like crazy?
And that's where it gets even more interesting. Now we have experiments showing a force similar to push gravity, the Casimir effect.
Oh yeah, the Casimir effect, that's a good one.
So what's the Casimir effect, and what does it tell us about gravity?
Okay, picture two plates really close together in a vacuum. You'd think there'd be no force between them, right? But the quirks of quantum mechanics mean these virtual particles that are everywhere actually push the plates together. It's like a tiny version of the shadowing in push gravity, minus the whole overheating problem.
So push gravity might sound out there, but there are these hints that it might have some legs.
Exactly, it makes you think.
And speaking of things that make you think, you sent in some wild experiments about actually controlling gravity. Clarino Majorana and his setup, it sounds like science fiction.
Majorana didn't mess around. We're talking massive lead shields, tanks of mercury, metal balls, all to see if he could block gravity. And get this, he claimed he measured tiny weight changes that fit with gravity being absorbed.
Whoa, that's nuts. And then there's Dr. Bueller, who said he got gravity to actually repel using negatively charged plates. But hold on, the author we've been talking about thinks positively charged plates are the ticket.
Makes you wonder, can we really control gravity? If these experiments are right, it changed everything about how we see this force and what we could do with it.
It's crazy to think we might be able to mess with gravity. But even if we forget about those experiments for a second, there are still huge cosmic mysteries that our current theories can't explain, like the galaxy rotation problem. It shows how even our most basic ideas in physics can get rocked by what we actually see out there.
Totally. Picture a spiral galaxy. You'd think the stars would orbit slower the further out you go, right? Like planets further from the sun.
Makes sense too.
But that's not what happens. The stars way out on the edge are moving way too fast. It's like there's some invisible stuff, dark matter, giving extra gravity to keep them in those speedy orbits.
And that's the leading theory, right? But we haven't actually found this dark matter yet.
Not directly. It's been hiding from us. Which is why some physicists are looking at other explanations like MOND, modified Newtonian dynamics.
I have to admit, MOND sounds kind of out there. It's like saying Newton's laws, which work great here on Earth, need a tweak when you're talking about the super weak gravity in those giant galaxies.
That's the gist. And here's the kicker. With just a tiny adjustment, MOND nails the galaxy rotation curves perfectly, no dark matter needed. It's a simpler explanation, at least on paper.
But this isn't just some fringe idea, right? This brief assessment you sent, it talks about Stacy McGaw. He's a big shot astronomer who used to be all about dark matter, but he switched sides after looking at galaxy data for years.
Talk about following the evidence, even if it shakes up your worldview. If McGough's right about MOND, it would change how we see the universe.
Like the universe keeps throwing us curveballs, making us rethink everything we thought we knew. And speaking of rethinking things, what about the speed of gravity? That gravity emerges, paper mentions Tom Van Flandern, he thought gravity might be way faster than light, maybe even instant.
Controversial, for sure. Einstein's special relativity, which is kind of a big deal in physics, says nothing can outrace light. But Van Flandern and others pointed out that if gravity followed that speed limit, we'd see funky stuff happening with the planet's orbits, a kind of gravitational lag.
So because we don't see those weird orbits, maybe gravity has a secret speed boost.
That's the idea.
Yeah.
And if it's true, who knows what it means? It could even link gravity to that other head-scratcher, quantum entanglement.
Well, hold up, quantum entanglement. That's where two particles are connected over any distance you touch one. The other one instantly reacts, even if they're light years apart.
Spooky action at a distance, Einstein called it. It seemed impossible, like it was breaking the speed of light. And that instant connection makes some people wonder if there's a deeper connection between entanglement and how fast gravity travels. Could they both be tapping into some hidden part of reality we haven't grasped yet?
My brain's starting to hurt. But then we have the author of Gravitational Mechanics going in a totally different direction. This idea of missing electrons being linked to gravity that's thinking outside the box.
Definitely unconventional.
Uh.
But they make some cool connections. They even try to calculate how many electrons are missing in the Earth and the Sun and propose a whole new equation for gravity.
And that plea to NASA in the rejection letter, you feel their passion, even if other scientists weren't convinced. But it shows how much we still don't get about gravity, and maybe we need to think differently to make real progress.
Like Niels Bohr said, we're all agreed that your theory is crazy. The question that divides us is whether it is crazy enough to have a chance of being correct.
It's funny, isn't it? So many of these sources, even the really out there ones, keep coming back to this idea of an ether.
Yeah.
The author of Gravitational Mechanics connects it to those missing electrons, and then nature of gravitation and ether gravity. They're saying ether pressure itself might be what causes gravity.
It's wild. The ether, this idea physics tossed out ages ago, it just won't quit. Makes you wonder if there's something there we missed. Some way to make it fit with what we know now about the universe.
It's like we've taken this whirlwind tour of gravity, from Newton's laws to Einstein warping space-time, from invisible particles to MOND, missing electrons, whispers of an ether, even gravity breaking the speed limit. And honestly, I feel like we've barely scratched the surface.
You know, maybe there isn't just one right answer about gravity. Maybe these are all pieces of the puzzle, each showing us a part of the truth.
It's a bit humbling, isn't it?
Totally. To realize how much we don't know. But it's exciting, too, to think we live in a universe with so much left to discover. Like Richard Feynman said, I can live with doubt and uncertainty and not knowing. I think it's much more interesting to live not knowing than to have answers which might be wrong.
So as we wrap up this deep dive, what's the one thing you want our listener to take away from all this?
I hope they come away with that sense of wonder about the universe and the courage to ask big questions, to explore the wild ideas.
Yeah.
Because it's at the edges where our neat theories start to unravel that the really exciting discoveries happen.
I love that. This deep dive has left me with way more questions than answers, but that's the best part. It's reminded me how much fun it is to explore, that the journey is just as important as the destination.
And who knows, maybe our listener will be the one to make that next big breakthrough, to finally crack the code of gravity. But until then, keep asking those questions, keep exploring, and never stop looking up at the stars.
Beautifully said. Thanks for joining me on this deep dive. And to you, the listener, thanks for sending in these incredible materials. Until next time, keep those questions coming.